Oh, hi everybody. We didn't see you in a long time. Welcome back to the math series, where it's all math all the time. Who's ready for some math? I know I am. You ready? Yes. You ready, Byron? No.
Here are.
You ready, Shauna? Oh yeah, I'm so damn ready. Come on, let's go. What are we waiting for? Wait. Where's Chicky? Oh, there he is.
Ducky? What?
Chicky, you're gonna love this. It's time for some math.
Whee! Woo! Ducky! Ducky! Oh, hi everybody. I'm Ellie the elephant. Welcome to the math series.
That's what we just said.
Oh, silly me.
Don't worry, it's not your fault. Today we are learning something very special. Something very special you'll actually get very engaged in.
Really? I don't believe you.
Come and see for yourself.
Ooh.
I wonder what it could be.
Ducky? Ooh. Coin.
That's right, Chicky. That's a coin. And today's math lesson is related to coins. Because, although we are not primarily talking about coins, we're talking about something that relates to coins. And that is called data and experiments.
Huh? What's that? I forgot again.
Data is lots of things that you collect from an experiment. An experiment is just a simple test to collect data and observe. You know, some people have to record, report, and yes, even observe a thing or two. Like Chicky. Chicky discovers lots of things, so he's very observant. Chicky, can you demonstrate your observance?
Ducky! Oh, Huh?
By observing the wheel go round and round, Chicky learns that circles spin round.
Ducky! Yaha!
And that's an experiment, determining what things roll and what things don't. The door doesn't roll.
Ducky! Yeah!
Because it's not round. It's rectangular in shape. So that's how Chicky demonstrates his observance. And today we're going to be observing a lot, because these experiments are usually hands-on. And they're very fun, too.
Come on out, Romeo and Juliet!
Ooh, this all looks new. I can't believe we're learning a new lesson. Come on out here.
Oh, sorry.
Vocabulary. Ooh, I feel like we're learning some new goddamn words today.
Yes, we are! Look! Sample space, experiment, outcomes. What do those words even mean?
That's a very great question, Juliet. For a situation to be a probability experiment, it must have more than one possible result.
Huh?
The possible results are called the outcomes of the experiment. The sample space is the set of all possible outcomes of a probability experiment. And an experiment is a simple test to collect data.
Wait a minute. So you're telling me that all the outcomes of the experiment are the sample space?
That's right, Juliet. The sample space is the set of all possible outcomes in the experiment. And the set of all possible outcomes is all the possible data that we can collect from the experiment. Yes. So, in other words, we can also tabulate the data. But, tabulation is a secondary data use, which we will not be doing. But we will be doing something similar to tabulating, which is definitely labeling out all the possible outcomes in something we call a sample space. You can think of the coin toss at the start of a soccer match to see which team goes first as an experiment. So you can think of it like a soccer match. Who goes first? Which team goes first? Like, for example, Team 1 and Team 2. Team 1 goes first, then Team 1 will probably either will or will not score a goal. Those are the two possible outcomes. Team 1 will either will or will not score a goal. See? Yes or no for scoring a goal are the two possible outcomes for Team 1, and it's the same for Team 2, because in soccer, you could really only just win or lose a game. So, win or lose are the two possible outcomes. W is for win, L is for lose. So each time the players lose, it's written as L. Each time the players win, it's written as W. It's the same thing as a coin, except it's heads and tails. So heads and tails are the members of the sample space. You can write the sample space as HT. Remember to use brackets to enclose the members of the sample space and commas to separate them. Those are extremely important, guys. Without those, it will not be a sample space at all. So you have to include those. Those are super crucial. Notice the H and the T here. What'd you notice about the H and the T? Why is there an H and a T in the sample space? Why do you think so?
Oh, we're flipping heads and tails. So I think H is for heads and T is for tails.
That's right. H represents heads and T represents tails. So the two possible outcomes of flipping a coin are H and T, because you could only roll heads or tails, and that because coins only have two sides, one side or the other. So they don't have any more. So they only have a front and a back. So that's only two surfaces so far. A front or a back, H or T. H is usually the front, and tails is usually the back. So F can be the front, B can be the back. But most commonly it's HT, because it's heads and tails. Rolling a 1 to 6 number cube to see how many spaces to move when playing a board game is another experiment. But this time with a lot more numbers, because the cube has a lot more surfaces. Look!
Oh yeah, I just noticed that.
Yes, a cube has 6 surfaces. So, what should the size of the sample space be? What do you think? From 1 to 6.
Well, I know it can't be 1, because it has a lot more than one surface.
Well, I can only see 1, 2, 3 numbers here. But I don't think it's 3, is it? No, it's not 3, because look, there's another face over here, and another face here. That makes 4 and 5, and the bottom face is 6. See? 1, 2, 3, 4, 5, 6. Remember in geometry, a cube has 6 faces? Yeah. So yeah, 6 equal faces. So we think that there may be 6 possible outcomes. And we are right. Rolling a 1, 2, 3, 4, 5, or 6 are the only 6 possible outcomes of the experiment.
Wait a minute. So you're saying that no matter how hard we try, rolling one 1 to 6 number cube will not get a 7 because 7 is not between 1 and 6?
Exactly. It's impossible to roll a 7 because this cube only goes up to 6. It doesn't go up to 7, so it's impossible to roll a 7. I see what you're saying there. Yeah. You can't roll 7 using a 1 to 6 number cube because it's all the numbers from 1 to 6, not from 1 to 10 or something, you know? And that'd be greater than 6, and we don't have any numbers greater than 6 on this cube, so that's why rolling a 7 is impossible for this event. Write the sample space for rolling a 1 to 6 number cube. Remember the brackets. These are the brackets that you should put in your sample space, and the commas to separate your outcomes. Now, rolling a 1, 2, 3, 4, 5, or 6 are the 6 possible outcomes, and the sample space is all the possible outcomes. Sibby, you try this one. What is the sample space?
Well, if we roll a 1, 2, 3, 4, 5, or 6, the sample space should be the numbers 1 to 6. 1, 2, 3, 4, 5, 6, right?
Yes, that's right. The sample space is 1, 2, 3, 4, 5, 6 in commas and brackets. Because, as we already mentioned, a 1 to 6 number cube has all the numbers from 1 to 6. So we just need to label the numbers. That's it. That's very simple. 1, 2, 3, 4, 5, and 6. That is the total sample space. That's all the 6 possible outcomes of rolling a 1 to 6 number cube. Rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, or rolling a 6. But not rolling a 7, remember, because it only goes up to 6, not to 7. So, yes, think of it this way. If you only have 6 sheep in a row, how can there be one more sheep? Huh? There are only 6 sheep to visualize here. And if 7 sheep get on there, it would break the rule, because 6 is not equal to 7. 6 is less than 7, so it breaks the rule. So rolling a 7 is impossible for a 1 to 6 number cube, because obviously it spoils. It's 1 to 6. It has a 1 to 6 in its name. 1 to 6 number cube. See? 6. That's a maximum number. 7's higher, so we can't use 7.
Ooh. Wait, that's a coin and a cube.
Exactly, Wally. Sometimes an experiment can have more than one part.
Oh, really?
Yes. Tossing a coin and rolling a 1 to 6 number cube is also an experiment. One possible outcome, H2, is tossing heads and rolling 2. This is because H stands for heads, and 2 means that we're rolling 2 from the number cube. So there's a 2 here. H2 is the probability of tossing heads and rolling a 2. Use parentheses to keep the 2 parts of an outcome together. So this is completely different from the brackets we use. So this time, we use parentheses for these 2 ones instead of brackets. Find the 12 possible outcomes of tossing a coin and rolling a 1 to 6 number cube. Write the sample space. So there are lots, and I mean lots, of different ways to tabulate this. But, we're just going to perform these ones. Rolling an even or an odd number is possible, because all the numbers from 1 to 6 are either odd or even. Remember 2nd grade, odd or even numbers?
Oh, yeah! We had to make the dots form pairs.
Yeah, and we're a pair.
Yes, we're 2 people. We're a couple.
That's right, 2 is an even number. So if we were to roll even numbers, 2 would be on that sample space, because 2 is an even number. Very good.
What about 0?
That is a very great question, Sibby. But there's no 0, because it says 1 to 6. 1 is the smallest number there. 0 is smaller. So again, it breaks that rule. If you only have 1 sheep, there aren't no sheep at all, there's just 1 sheep. So again, if there are no sheep, that would break that rule. Because 0 is not equal to 1, remember that it's a mathematical error. 1 is greater than 0. So we assume that we cannot roll a 0. It's impossible to roll a 7 or a 0, because it's 1 to 6, not 0 to 7. So that's why 0 is not an answer. But 0 is an even number. Although it does not form any pairs because it has nothing, but I mean, hey, what do I know? Anyways, 10 is an even number and ends in a 0, and 0 ends in a 0, so that pretty much makes sense. Okay, even numbers include 2, 4, and 6. So the sample space for rolling an even number on a 1 to 6 number cube is 2, 4, 6. That's because the numbers 2, 4, and 6 are all even numbers. That's because they all are divisible by 2. 2 divided by 2 is 1. It's kind of like you guys. You married couple guys, Romeo and Juliet. You guys are a pair, but you are only one pair. That's 2 divided by 2 people. And that's 1 person in each group if we were to split it equally. 2 divided by 2 is 1. So that's an even number. Now that's what I call a fair couple. Aww. But if we have 2 couples together, that will be 4. And 4 divided by 2 is 2. There will be 2 2s. And then for 6, that would be 3 couples at once. 3 divided by 2... Wait, sorry, no. 3 times 2 is 6. So 6 divided by 2 is 3. So they're all divisible by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. And 6 divided by 2 is 3. So half of 6 is 3. Half of 4 is 2. And half of 2 is 1. So it's very easy to see that taking half of something is usually dividing it by 2. So, yeah, that's pretty much how it works. That does make sense, because we could split apart. Yes, there are times where we're separated. And look, I'm one person.
And I'm one person.
If we come closer together, we feel like we're attracting.
Yes.
And we form a pair. That's 2 people in one group. That's already 2. There's no more than 2 of us. Ah. And 2 lips. And that is sample space. We can also do odd numbers. Odd numbers are numbers that are not divisible by 2 or have 1 left over.
Ducky?
Yes, Chicky. Can you try and find an odd amount?
Ducky? Ducky! Ducky!
That's right. 1 is an odd number. Good job. That's 1 ball. This is only 1 ball. And although it is only 1 ball all by itself, it cannot form any pairs because it is alone. Visualize it this way. It would probably be very sad to be alone, right?
Yeah, then you will just be 1 you. And there won't be anybody else. It's just 1.
Yes, exactly. 1. That's why 1 is sometimes called the loneliest number. It's all alone with nobody else. But then if another 1 comes...
That would be 2.
And 2 is better than 1.
Aw.
Yes. And actually, fun fact for you guys... When 2 balls lightly touch each other, that's called a kiss.
Really?
Yes. When 2 balls lightly touch each other, that's called a kiss. Look. Aww. I don't think it's the kind of kiss we engage in. No, it's not that kind of kiss. But, thank you for demonstrating anyway. It's very good to use analogies to remember stuff better. And I think we should use that way more often.
True.
So let's put these balls back. Balls. Okay, now there's 1 ball left. And you're right, Chicky. 1 is an odd number.
Ducky!
So, if we want to roll an odd number on a 1 to 6 number cube, 1 would be one of the numbers. Next would come 3, because 3 is not divisible by 2 as well. And 5 is not divisible by 2. 7 is not divisible by 2. But remember, it's a 1 to 6 number cube, not a 1 to 7. So, we can't get a 7. Again, there's 6 sheep, no 7 sheep. So, yeah, making it 7 sheep would break a rule. Because 7 is not equal to 6. Remember. So, that's why it's impossible to roll a 7 or a 0. Because it's not a 0 to 7 number cube. It's a 1 to 6 number cube. You see, people? We also have lots more. Like prime numbers. Like rolling prime numbers. You remember prime numbers? Prime numbers are numbers that only have 2 factors. Chicky, can you find me a prime number?
Ducky? Oh! Ducky! Doo-doo.
You're right, Chicky. 3 is a prime number. Good job. Because we need to make a rectangle with 3 as much as we could. So, that is 3 by 1. 3 balls wide by 1 ball tall. 3 times 1 is 3. But how about 2s? The 2s don't work. So, 3 is prime. And since 2 is the only other number that comes before 3, We're done already. 3 is a prime number. We don't need to do any more steps. So, like this, let's arrange the balls. There are 3 groups of 1 ball. 1 ball in each group. 1 plus 1 plus 1 is 3. So that is all even. Although the number really is odd. Cuckoo! That's right, Cuckoo. It's just 3 lots of 1 all squashed together. That's 3. But we can't combine it with the 2's because that's 2 plus 1, and 1 is not 2. So there's 1, 2, and 3, and 1 left over. So that makes it an odd number. And then 1 ball wide by 3 balls tall. 1 group of 3. That's already 3. 1 times 3 is 3 times 1. And we can't do it with a 2 because it's an odd number. So yes, 3 is a prime number. So, you're right, Chicky. If we were to roll a prime number on this 1 to 6 number cube, 3 would be one number from the sample space because 3 is a prime number. Also, 2 is a prime number. What? But it's even! Yes, but 2 is the only even number that is prime. All other even numbers have 3 or more factors, guys. You should know this. So, 2 is the only even number that only has 2 factors. All other even numbers that are greater than 2 will have 3 or more factors. So, let's take these balls, for example. So, 2 balls wide by 1 ball tall, 2 times 1 is 2. Let's think of the Romeo and Juliet scenario again. If we split them apart again, that's 1 group of 2. But then if we split them into 2 groups of 1, that's already even. 1 person in each group. Romeo in that group, Juliet in the other group. It's the same thing, but with the balls. Let's pretend that this ball is Romeo, and this ball's Juliet. That would be almost the exact identical scenario, except with different visuals. So 2 lots of 1 gets 2. So, yes, they attract each other. That would make 1 group of 2. Same thing with those 2 people. They attract and form a couple, which is another word to say 2. And, 1 is the only number that is before 2, really. So, we can divide it into 1s and 2s only. So, that's pretty much it. We can't do it diagonally, because that's not a rectangle at all. We could do it this way, though. That'd be 1 ball wide by 2 balls tall. That's 2 as well. So 1 times 2 is 2 times 1. There are only 2 ways to make 2. 1 plus 1, or 2 on its own. So pretty much there's only 2 rectangles that 2 can make. 1 by 2, or 2 by 1. So that's how 2 is a prime number. So if we want to roll a prime number from a 1 to 6 number cube, 2 would be the other number. However, that is the opposite when we compare it with composite numbers. If we want to roll a composite number from a 1 to 6 number cube, 4 would be one of them. You want to know why? Because if we put 4 babies over here, Wally, Fudgy, Ellie, and Mango, in a square, do you notice that there are 2 of these baby couples? We can split them up. 2 on this side, and 2 on the other side. That's even. 4 divided by 2 is 2. 1, 2, 1, 2. 1, 2, 3, 4. And since 4 is an even number that is larger than 2, it's composite. 2 is the only even prime number. Remember this. You should remember this. So, since 4 is even and is larger than 2, it is a composite number. 4 is a composite number. 4 is not prime. We can prove this by finding the square root of 4, but that's just 2 because 2 lots of 2 make 4. So, yeah, if we were to roll composite numbers on a 1 to 6 number cube, 4 would be one of the numbers. And 6, too. Because remember, 6 is also an even number. Let's bring Romeo and Juliet. That would make 2 more people. Come on, guys. So 2, 4,
and 6! Oh boy, we're really part of the mix.
Now there are 2, 4, 6 people over here on the line. That makes a rectangle. 2 people wide by 3 people tall. 2 by 3. That's 6 already. Which means they're also 3 by 2. Which is also equivalent to 6. Yes, that's equivalent to 6 as well. 2 times 3 is 6, and 3 times 2 is 6. Also, 6 is an even number that is larger than 2. So guess what? It's already composite. So 6 would be another number we can use. So, yeah. 1 is not prime or composite because 1 only has one factor, which is itself. Consider it like one ball. There's no other balls around here, right? Just this very one. That's only one. Only one possible way to make 1, which is 1. That's the one that is 1 there. I think we're over 1ing this. Oh! Anyway, there's only one way to make 1, and only one rectangle that 1 can make, which is 1 by 1. And 1 is the same number as itself. So 1 only has one factor. Itself. 1. That's it. It's only 1. One factor. Prime numbers should have at least 2 factors, but 1 only has one factor, so it's not a prime number. Composite numbers should have 3 or more factors, but again, 1 only has one factor, and 1 is less than 3 and 2. So 1 is not a prime or composite number at all. It's a very special number called a unit, or a unity number. A unitary number. What? 0 is also not prime or composite because it's not positive or negative.
Wow, I didn't know that.
Yes. This is nothing. This is 0. There's no way to make 0 other than showing nothing. So that's not prime or composite either. Because there's really nothing there. It's nothing. Anyway, what is the sample space for an experiment of tossing 2 coins? Well, we know that the sample space for rolling 1 coin is HT, so HT again! 2 coins, 2 of those HTs. So would it be HT, HT? That's right, it would be HT, HT. Because there are 2 H's and 2 T's. And for 2 coins, 1 coin is either H or T, and the other coin is either H or T. Both of those H's and T's already meet. So, those are the 4 possible outcomes. Again, 4 divided by 2 is 2. 1, 2, 3, 4. 2 letters in each coin. 2 letters, 2 letters. That's all 4 letters. So, that would be HTHT. The size of that sample space would be 4, because there are 4 possible letters or outcomes for rolling 2 two-sided coins. You see? That's how we can better understand how to do an experiment very well. Okay, you can come back, Chicky.
Okay, Roo.
I know, you really like playing with those balls. We'll play more with those balls later. There are other ways to represent sample space. For example, you could pull letter tiles out of a bag, like this, A, B, C, D. Or again, the number cube example. We really like the number cube example. It really keeps me innovated, you know? It ties me up with all those abstract numbers. Let's look at this scenario. A drawing, a table, and a tree diagram are all ways to represent the sample space for an experiment. So a drawing is a representation, we should all know that. A table is a kind of diagram. And a tree diagram, we're going to get to that in a second. You're going to love the tree diagram. Rick takes 1 letter tile from a bag and rolls a 1 to 6 cube from a probability experiment. He puts the tile back in the bag each time. Rick wants to represent the sample space. Rick makes this drawing to show the outcomes. Okay, this is the drawing. The drawing is one of the possible ways to tabulate the results of the experiment. Again, the basic form of tabulation. tabulation is the process of just collecting data and representing it in an experiment. So this is what tabulation looks like. A1, A2, B2, B1. See? Look at all those numbers. And do you notice how many there are in each column and row? Yeah, look at it. 1, 2, 3, 4, 5, 6 this way, and 1, 2, 3, 4 this way. 6 by 4. Anybody know what 6 by 4 is?
Look at it this way.
2, 4,
6.
but 4 times. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So 6 times 4 is 24, right?
Yes.
Because 6 times 2 is 12, and 6 times 4 is double that of 12. And double 12 is 24, because 12 plus 12 is 24. So, the possible outcomes that Rick's experiment has is 24. Let's double check to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We guessed right! And plus, we should all know this if we count the dots carefully. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's half. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we counted right. There are 24 possible outcomes. So, there are 24 possible ways that Rick could perform this experiment. Getting out a letter A or rolling a 1, getting out a C or rolling a 4, or getting a D or rolling a 6. It lists them in order from tile to number. So first, the tile goes first, and then the number goes second. This goes on top of this one. On top is really like first. Like first place, when you win first place, you're at the top. So this is at the top of the cube. This is usually first place, second place. Second place is below. So, yeah, that's how you can represent not only rankings, but also how it is ranked. Complete the table of outcomes for Rick's experiment. A table is another way to represent it. It has this tile number along with this tile number. This is the tile section and this is the number section. Those aren't tiles, these are numbers. So that makes lots of sense. Chicky, can you come over here and try to fill in the missing spaces?
Ducky!
What do you think comes after B1?
Ducky?
That's right. B2 comes next. But why? Look at it this way. What is 1 more than 1? 2. Oh! B2 can be thought of as 1 more than B1. B1 plus 1 more of those B1s makes B2. So 1 plus 1 is 2. So 1 of those B1s plus another 1 of those B1s makes B2. Like 2 of those B's together. And then 2 plus 1, 3 B's, B3, B4, B5, B6. Oh, and if that's true, then A4 comes before A5. And A6, too. C1, C2, C3, C4, C5, C6. And that means D1, D2, D3, D4, D5, D6. Yes! We figured out the pattern. It's increasing 1 more every time, per letter. Rick also draws a tree diagram of the outcomes. Now, this is the fun part. I promised this part, and it's guaranteed. This is a tree diagram. You all want to know why it's called a tree diagram? It doesn't look a lot like a tree. Ah, but watch closer. What else do you see in the tree diagrams? Oh, I see little arrows or stick thingies pointing towards the numbers. Yes, exactly. What do those stick thingies represent to you? Oh, I get it now. The sticky things are pointing down at the bottom. And trees have sticky things that point down at the bottom, which are the roots, right? Yes, those are the roots. That represents the roots of a tree. The tree diagram represents the roots of a tree. So breaking it down is just like going down the tree from its bark to its roots. That's breaking it down. So A can be split into these possible options. So are B, C, and D. The tree diagram represents the outcomes down in order, like the roots of a tree. So you see, this can be the top of the tree, and this can be the bottom of the tree. Like, the tree gets water from its roots, right? We all should know that in science class. Trees need water to survive. If the water is implemented in, that is, if Rick rolls the dice more times, then more outcomes will be implemented. It would be like more water is coming into the tree. More water to make the tree grow. Or more outcomes to make the roots grow into more roots. 6. If we add a 7, then it would be 7. But it's not 7 because it's impossible. Remember? 1 to 6, not 7. But if we would add 7, then it could be 7. And there are 24 possible outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 possible outcomes. Yes, 6 lots of 4, 4 lots of 6. That's the same as 24. Woohoo! So now we can solve problems about sample space. Sometimes there are lots of problems on the way. First coin, second coin, and third coin. Sometimes you can toss 3 coins and still do not know what you're going to end up with. But don't worry, I'll show you what it takes. Look at this H up here. What are the possible outcomes of rolling a coin after you hit heads? Heads and tails, right? Because it's only 2 other outcomes. But then that H will get broken down into an H or T. And that T will be broken down into an H or T. So that's H, H, T, H, T, H, T, which makes 1, 2, 3, 4, 5, 6, 7 possible outcomes for this one. And then 1, 2, 3, 4, 5, 6, 7 outcomes for this one. T, H, T, H, T, H, T. So the total sample space is H, H, T, H, T, H, T, T, H, T, H, T, H, T. Because H, H, T, H, T, H, T, T, H, T, H, T, H, T is the order of H, H, T, H, T, H, T, T, H, T, H, T, H, T. Almost messed that up. Count the possible outcomes. All right. We all should know how to count, right?
Here are.
I'm just kidding. We all know how to count. Trot. Let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 possible letters. So what's the size of the sample space? 14! That's right, Squeak the Mouse. That's 14 possible outcomes for the total experiment. Find the size of the sample space for an experiment of rolling 2 1 to 6 number cubes. Well, that's fairly easy as well, because really, there are 2 lots of those 6 possible outcomes. And what's 2 lots of 6? 12? That's right, 2 times 6 is 12. So the size is 12. Great job, guys. I think you're getting the hang of this. Now, we look at events. What is an event? That's a very good question to ask. An experiment, such as rolling a 1 to 6 number cube, may have different events. An event is a set of outcomes that includes all related members of the sample space. So, if the event is roll a 1, then the related members of the sample space are 1. That's it, because there's only one number in that event, which is 1. So we only need to put in one related member of the sample space, which is only 1. Roll an even number, that would be 2, 4, and 6, because 2, 4, and 6 are all even numbers. Roll 3 or 5, those are 2 numbers, so 3 and 5 are the members of those. So, What members of a sample space for rolling a 1 to 6 number cube are related to the event roll an odd number? Well, I think we just did that. It's 1, 3, and 5. Because 1, 3, and 5 are all odd numbers. Think of the alone scenario again. It's sad to be 1 by yourself and alone. Unless there's another person making 2. Aw. See? That's kind of like the R&J scenario, to put it, for all you unfamiliar people out there. 1, 3, and 5 are all odd numbers because of this. Because although 3 already has a 2, it cannot form another pair because that's 2 plus 1, not 2 plus 2, not 4. So that's an odd number because it's not divisible by 2. 3 is not divisible by 2. And neither is 5, nor 1. Hence, we can prove it's true that 1, 3, and 5 are all odd numbers. What members of the sample space for tossing 2 coins are related to the event 2 heads or 2 tails? There are several ways to put this. We could do it in 2 ways. Number 1, 2H, 2T, because 2 H's or 2 T's, or 2, most commonly, HHTT. See? 2 H's and 2 T's. That's very, very simple. That's all you have to do. Write the related members of the sample space just to get the hang of this. So for coins, it's letters. For a 1 to 6 number cube, it's numbers. Because, obviously, the number cube has a number in its name. Number. So, it has number in its name, so that's numbers. Okay, now we also can represent this experiment with spinners. Have you ever heard of wheels? Those wheels with arrows are very fun to spin around. The 4 colors of the spinner are red, yellow, green, and violet. Notice all those black bolded letters at the beginning of the word red, yellow, green, and violet. What do you notice about these? These are all capital letters. Maybe we can represent this with a drawing. And we could. Violet has a V in it. Remember kindergarten? The beginning letter of a word. The beginning letter of a word is always the first letter of the word. Let's recap back. I know, you all are going to know this. But I just love this Touch and Teach turtle toy. I don't know, it's probably the 2008 version. I'm still not sure. Alright, when you were kids, not all of you played with this, but some of you did. You knew that the beginning letter of each word is the first letter of each word. So, violet starts with V. Dog starts with D. So that's D first. Violet starts with V, so we draw V over there. Green starts with G, so we do G. And goat starts with G, so we put G in there. Yellow starts with Y. Y is another possible outcome because yellow starts with Y. And R is for red. So, yes, we can tie 6th grade math back to kindergarten concepts if we can recall beginning letters. You see, it's all that simple. All you have to do is tie the concepts together and then come up with a solution. So you see, rabbit begins with R and red begins with R. That capital R looks almost the same letter as this capital R, except with much thinner bodies. So, yeah, those are the beginning letters to identify each color. Alright, sorry, Touch and Teach Turtle, you have to go. Common crash. Anyway, the outcomes are G, Y, R, and V. How many letters is that? 1, 2, 3, 4. Those are 4 letters. So the size of this one is 4. Now, we do this one. H, T, H, H, T, H, T, H. This is an optional one because really only one coin is just rolling 2 of them. For every 2 heads, you toss 1 tail. Am I wrong? Let's just check and see. H, T, H, 2 H's, 1 T. H, T, H, 2 H's, 1 T. H, H, T, 2 H's, 1 T. So no, I'm not wrong. For every 2 heads, you toss 1 tail. So that is a possible repeating pattern. H, T, H, H, T, H, H, T, H, 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 T, or T, H, H. You know? Every way you go, there's always going to be a T. There's never going to be just H's. So, yeah. Or T's. That would be YVGRHTHHTHTH. That would equal the sample space. And the size would be 12 because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters are in the set. Let's look at this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters. That would make 12 as the size of the sample space. So, it's the same thing for the event. Spinning yellow and tossing H would be Y and H. That's the same thing for red H and T. It's red H and T. Very simple. Just implement those there, and you could become a sample space scientist. Okay, guys, that's it from us today. We are officially out of time. I hope you enjoyed this very long math segment. And I hope that Romeo and Juliet did too. Did you guys enjoy it?
Yeah, it was quite a blast.
Yeah. It was Montague Math.
You're so funny.
All right. Come back another day to see another math lesson. We promise to post another math lesson to you, but it may take a while. So please don't be afraid if we're lagging for some reason. That's because we're just behind on some other deadlines. Okay? Alright, that's it from us today. I hope you enjoyed this math video. And always remember, think win-win, not win-lose. Because as long as you're learning, and as long as you're taking part in something, you're already a winner. Alright, guys. See you later. Bye.
Bye. Do 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 do.